Well, hello everybody. I am just going to make a very fast video this time. The reason for doing this is so that you're able to do those homework problems for Monday rather than having to wait until Monday before you can really think about those problems. The idea is I want you to be mostly ready to start reviewing for the test by that time, not having to learn a whole bunch of new stuff. So there's going to be a little bit of new stuff next Monday, but if I do a little bit now, it's going to actually make things, I think, better for you as we go forward. So it turns out, we were bragging about the determinant in class and saying that, well, it's a test for invertibility. So if the determinant of a matrix is not 0, that means the matrix is invertible. And we learned kind of how to compute determinants using 1 by 1, 2 by 2, 3 by 3. We have formulas for those. Otherwise, we can use that cofactor expansion theorem. Well, it turns out that not only is the determinant useful for deciding if a matrix is invertible or not, it actually also can be used to come up with the inverse. So we can find the inverse of A by using what is called the Adjoint method, which is going to use the determinant concept that we learned about in class. So I'm just going to write down a couple quick definitions and do one example, and then you're going to be able to handle all of those problems that are in the assignment. So the first one is just just a quick definition. What is the matrix of cofactors? So here's the idea. If every element of A, so we take the matrix A, which is a square matrix, of course, if it is replaced, if every element of A is replaced by its cofactor, so in other words, we're going to replace Aij with Cij, the Ij cofactor. If we replace every element by its cofactor, we get what is called the matrix of cofactors. And that's usually written M sub C. So the matrix of cofactors. All right? And then just as a quick follow-up definition, it turns out that the adjoint of A, which is what you see at the top of the board, the adjoint of A is just simply, we write that as AdJ of A equals, what you do is you simply transpose the matrix of cofactors. Okay? So let me give you a quick example. So the matrix of cofactors, you're just simply replacing the elements of the matrix with the corresponding cofactors. So here's an example of a matrix: 2, -3, 0, 2, 1, 5, and 0, -1, 2. Okay? What we're going to do is try and write down the matrix of cofactors. Okay? So the matrix of cofactors is just the matrix, C11, C12, C13, C21, C22, C23, C31, C32, C33. Right? Okay? So let's just work this out for this example. It's really not too difficult. So for example, the 1,1 cofactor, we basically are crossing off. Remember, it's basically the same as the 1,1 minor. So you cross off the first row and column, and you get this little 2 by 2 matrix down here, and you take the determinant of it just using the AD minus BC formula. You see that it's 2 minus -5, which is 7. So the 1,1 minor is 7, and in the case of that position, you don't need to change the sign. So the cofactor is also 7. Okay? What about the 1,2 cofactor? Well, for the 1,2 cofactor, what we're going to do is cross off the first row and column, and we're going to leave ourselves with these 4 numbers, right? And the determinant of this little 2 by 2 is just 2 times 2 minus 0. So that would be 4. However, so the 1,2 minor is 4. That means the 1,2 cofactor is -4. We have to change the sign on that entry. Okay? What about the 1,3 cofactor? So I cross off the first row and last column. I have this little 2 by 2 matrix here. The determinant of that is just -2. So all of these determinants are just little 2 by 2s, so it makes it pretty easy to calculate. Okay? Let me go a little bit faster through the rest of them. The 2-1 cofactor is going to end up being 6. Basically, you take these 4 numbers here, which has a determinant of -6, but I have to switch the sign to +6. The 2-2 cofactor is going to be 4. The 2-3 cofactor is going to be 2. I'm going to let you guys check this on your own. Make sure you understand how I'm getting these numbers. The 3-1 cofactor looks like it's going to be -15. And the 3-2 cofactor is going to be -10. And the 3-3 cofactor is going to be 8. Okay? So that's the matrix of cofactors. And then, therefore, the adjoint is just the transpose of this. So I just take this matrix, the first row becomes the first column, the second row becomes the second column, and the third row becomes the third column. That's the adjoint of A. Well, what does that have to do with finding the inverse of A? Turns out we have a nice formula for the inverse of A, and I'm going to wait until class to explain the formula, but I just want to state this formula for you now so that you can just go straight into the homework. It's really easy. It just says that the inverse of A is just 1 over the determinant of A, which is a number, scalar multiplied on the adjoint of A. Okay? So we just have to, this is always true. We just have to take the adjoint of A and divide by the determinant of the matrix. This is a 3 by 3 matrix, so we can probably get the determinant pretty quickly from the arrow method. I'm going to go ahead and write down the terms. We're going to have 4 on the first arrow, the second arrow will be 0, the third arrow will be 0. Then subtracting in the opposite direction, we're going to have 0, and then minus -10, which is the same as +10. And then the last one is going to be minus -12, which is the same as +12. Yeah, okay. So 4 plus 10 plus 12 is 26. Okay? So the final answer then for the inverse of this matrix, isn't this beautiful? It's just 1 over 26 times the adjoint. Okay, so we just, very simple, we just have to learn how to calculate the matrix of cofactors, transpose it, and then divide by the determinant of the matrix. If we had tried to find this inverse by using the Gauss-Jordan method from chapter 2, look how bad the fractions would have ended up, right? This would just be the left side of that block process that you use for the Gauss-Jordan method. You would have some pretty nasty fractions. It would be pretty tough to get the right answer without making a mistake. The advantage of the adjoint method is that the fraction, which is the 1 over the determinant of A, kind of gets factored out, right? It's out in front of the adjoint matrix itself, which means that you don't really have the clutter of those fractions in the way. You see, there's no fractions anywhere here when you're doing the bulk of the work. It just has to be put down as a fraction at the very end when you divide by the determinant there. But it's pretty simple. So you have a few homework problems on this. I will explain this formula next time in class. Don't want to do that right now. I just wanted to give you a very brief explanation for how you can find A inverse using the determinant material and the cofactors that we learned about in class in the most recent lecture. So hope this helps, and if not, if you have any questions, definitely feel free to ask away and let me know. Thanks a lot.